What's up, what's up? Welcome back. Today we're working on my x86 operating system. So we have an operating system that runs in like a virtual machine. We've been developing on stream. We kind of have this like semi-functional, it does something OS. So hold on, let me just make sure I'm in clean state. Let me just back out to somewhere where it was working correctly. So here we can like run this demo that boots up our kernel from grub. It launches in QEMU. We have like a little game showing that we have like keyboard input, we have like graphics, we have logging to serial, and we have like some form of like network stack. If I like try to talk to my thing over TCP, it can like see that I got TCP data and it can send it back to us. Great. What we're working on right now is we're working towards like multi-core support. So right now, all of this is happening on one core, and we use Rust's futures to help us like kind of manage the fact that we're doing multiple work at once. So we don't have like threads, and the operating system isn't like context switching and doing preemptive context switching where it says like, oh, I'm gonna like remove this thread of execution and replace it with this one. What happens is we have like cooperative multitasking where each function will kind of say, hey, I'm done what I need to do right now. I need to wait for some stuff. Like I'm waiting for an Ethernet packet to come in or something. Like go do something else while we wait. And that's working pretty well. And what we're trying to do right now is we're trying to like break up our work into smaller chunks. So last stream, we got to the point where we split up our future executor, where future is like Rust's async chunk of work. We used to kind of have like one thing that was like demo. And within demo, we had like TCP and we had like game. And what we did last stream was we kind of like, instead of making these like a hierarchy of work, we kind of made like a area where we kind of like put these guys in one by one, and they can like now are seen by the system as two independent tasks that they have to run in parallel. Which means that like if we get towards multi-core, we can like pull individual ones of those tasks off one by one, instead of having like just one black box of large amounts of work. And that's working good, except now we kind of have this case where we have like Ethernet, for example. The Ethernet subsystem might like send stuff over to the TCP subsystem, and this communication needs to like signal to the TCP system that like there's work to do now. And what happens is the Rust system, what it does is it has like for each task in here, T1, T2, it has an associated like waker, we'll call it, like W1, W2. This is like how I've written it, how we wrote it last stream. And what happens is, if task 1 is like TCP and task 2 is Ethernet, Ethernet's supposed to poke this guy to say, hey, it's time to run task 1 again. Like, we know you're waiting on something from us, and like we've provided it to you. And that's, we've kind of like neglected that to some extent in our previous implementation because it didn't matter. Or like it mattered, but it wasn't like causing us any problems. And now those problems are becoming very clear. Because before we only had one task. And so if anybody woke up W1 at all, everything would get done again. And so now we're like seeing the consequences of skipping some of that work. So what I want to do today is like we have like some cases that are not working correctly, and we need to work through them. So if I remember correctly, when we ended last stream, yeah, we just have this like, our game isn't running. So if I like touch keyboard, sometimes it'll move like a little bit. Right, like here, I can get to go a couple frames at a time. But we're not seeing like constant progress like we should. I think also if I try to run like our TCP demo with the latest, we're not seeing any frames come in. And so we wanted to start trying to like debug which areas aren't correctly handling what they need to handle and fix them. Yep, and so that's what we're doing today. So that's intro done. And probably the first thing that we want to look at is we know that mutex unlocking does not wake waker. So we have like this like async mutex. And the way it works is pretty straightforward. He's got some data of any type, and he's got a count of how many people are accessing him, which should only ever be one. This could also be done with an atomic bool. In fact, it probably should be done with an atomic bool. And what he does is he just checks like, hey, does anybody have this count? Has anybody tried to? Is anybody holding this right now? This mutex? And if the answer is yes, then we say, okay, we can't get it right now, and we'll try again later. Otherwise, we try to increment, and if that increment fails, then we also say, okay, somebody else has it. Otherwise, we say, okay, it's ours now. We got it. Great. And then we get our mutex guard, and we can access the data. And when we drop it, we decrease the count again. Great. But an important thing to think about here we have this, like, when we try to lock, we also have this, like, wait for the count to decrease. Alright, so he says, oh, we should, like, attempt to acquire the mutex if the lock is free. And what we need to do here is we need to register a wake up with the mutex guards that are already held and signal back to this future that we just signal back that we should run it again to like the future executor system. And so we probably will need to do this in like several places. And so I was trying to think of like, we need like some sort of like generic abstraction for this probably that has like registration of like one to many wake ups, right? So like we might have like 5 people waiting on a mutex and 5 people who want to be notified when the mutex is available. Or maybe we should only maybe notify one of them because only one of them should actually try to acquire the mutex. And that starts to sound a little bit like a condition variable maybe, where you have this like system where you can ask the OS to tell us when we're ready to go. Or maybe like we'll call it like a notifier. Not really sure. So I think I'm just going to start like poking through to figure out what that would look like. So one thing I'm certain of is that our mutex guard, i.e. the like locked version of this thing, he's going to have to, when he destructs, he's going to have to unlock the not just unlock the mutex, but notify the other guys. So he's probably going to have some sort of structure that's like wake up list, and we'll just call it like a wake up list for now. I don't really know what this type is going to be, so for now I'm going to say type wake up list is equal to this. Just nothing. And then here's something we're going to have to do like wake up list wake up or notify one maybe, right? Like we want one person to attempt to acquire the mutex now. Or maybe we want like notify all and we just want them to race each other again. But notify one's probably good enough. So that means that our wake up list has to be some sort of like type that's a wake up list. And he has to have an implementation for wake up list. And for now, we'll just say that he's like a struct with no data because we don't know what the data is going to look like. And we'll just stub out the functions that we want. So we know we want a notify one that takes in self by immutable reference, maybe? Yeah, that seems reasonable. So maybe this will be a reference to a wake up list because he won't own it. And he is unimplemented. Great. What doesn't he like here? There is something wrong here. Oh, he needs derived debug. Or the debug implementation and unimplemented. There we go. Okay, so now we also know that on creation of a mutex guard, we're going to want to want to like register ourselves somehow as a specific person who's waiting on the wake up. So maybe we want like each person who's waiting for a mutex will probably want like a wake up list guard or something. The idea here is that when this guy is dropped, he's going to want to say, okay, I'm not waiting anymore, right? Like we only are waiting while this is alive. So probably he's going to have some sort of like wake up list, wake up guard. Well, we might like refine the names later as we go. And here he's going to, on the first pull, he's going to register himself with the wake up guard. So he's going to say self wake up guard register, and he's going to register his waker. So the Rust futures, they give us like a waker as part of the poll, future poll, right? So here they say, we're gonna like see, are you ready? Like, are you done? If you're done, great. But if you're not done, here is like a handle to like a way to wake me up to ask you if you're done again later. And so we're gonna like register this guy probably, and I think we have to clone him, which means that this guy needs an API to say register, and he's gonna take in himself by mutable reference is probably fine, I think. Because we'll only have one guard per feature, I think. We'll figure this out later. But I think mutable's fine. And then he's going to take in a waker, which is a waker, which is given to us by the Rust core feature stuff. And this is also unimplemented. Okay. Now, the wake up list is probably going to be associated with the mutex itself. That seems reasonable. Okay. And that means to get a guard, I think we call it wake up guard, is equal to, like, we'll ask our wake up list for a guard. Or a, yeah, we'll say a guard. Guard's probably the wrong word. Maybe we'll say handle, right? A handle to the wake up list that we can register a waker with. That seems reasonable. And he gives back a wake up guard, which we are now going to call a wake up handle. We like that term better. So let's just rename this really quick. This is wake up handle. Cool. So the mutex guard will take in a wake up list that is just our wake up list, right? And here, this guy's going to take in a wake up guard, which we wanted to rename to wake up handle. There we go. Okay. So here, what doesn't he like? Cannot mutate immutable variable self. So I think I just wrote mute here. Cool. And 68, we need to add the wake up list. So for now, we just say wake up list is a wake up list. And I think we compile now. Cool, we compile. Okay. So now the question is, what else do we have to do here? So we have to make a drop implementation for this wake up handle. And on drop, he's going to have to unregister himself. And so here we just have to say unregister myself with the wake up list. Here, we're going to register ourselves with the wake up list. Here, we're going to construct an ID or something. Okay, yeah, I think that seems reasonable. And so here on notify one, we're going to have to like pick one to notify. So probably what makes sense here, we'll say that we have wakers, and maybe they have they have IDs, and those IDs map to values of some form. Wakers, probably. We need to include hash map. So we'll just do that really quick. And this probably needs to be reference counted and locked, like mutex locked in some way. Sorry, I'm just noticing that my camera is really low frame rate. One sec, let me go turn on the lights. Think that's better? Okay. Yeah, so let's say that for now we have like hash map of ID to waker. And probably when we create a handle, he's going to have an ID. And we'll say wake up handle. ID has to be a unique ID, so we're going to say let ID is equal to self ID, and we're going to increment self.id. Which means here we need ID like this. And we need an ID in here. Okay. So we have to like make a constructor for our wake up list. And so he's gonna return a wake up list with an ID of 0 and a wakers list of empty. Great. And here, somewhere where we construct him, we have to call new on him. Okay. This wake up handle function is a problem because he has an ID that is trying to be incremented. So I guess this has to be an atomic U64. So that because I don't think we can make this mutable because I think this is going to be used from like read-only context. Atomic U64. Apparently it doesn't like that. Maybe there is no atomic U64 on 32-bit systems. Which means that we actually might have wraparound, which sucks. That's okay. For now, we'll just, ugh, that's annoying. I was kind of hoping that we could have enough, with a U64, I feel like there's enough numbers where we wouldn't have to worry about running out. But with a 32-bit one, we actually might. Which will be annoying. So maybe this wakers thing won't be, a hash map. I wonder if there's a way to there's probably a way to manage this in a vector so that we can use the IDs of the indexes into the vector as the IDs. So let's just try looking at what that would look like. So here we need to use the alloc vec so that we have a vector type. And here we would say that our ID is equal to self.wakers_len. And then we nope, that'll be a problem. Because we don't actually have the waker at this point. So maybe we have like a wakers that are a vector of option waker, right? Its initial thing is none, we allocate space for it, and then when we get an ID, push one in. We also would have to like walk this vector and look for maybe what happens when we drop. We would have to somehow like adjust the IDs of all of the all of the existing wake up handles. Unless we do like a swap and pop, then we only have to update the ID of one of them. So that seems reasonable. Maybe in each of these, we'll have a reference to the handle ID. So we have like arc, atomic usize, and a waker. So the idea here is that if we move these like elements around in the vector, we have to modify the ID in the handle side. That seems maybe reasonable. Well, let's look at how that would look. So our wake up handle would now have a ID that is an arc atomic usize. When we insert a new one, we would just put our ID is the length. We need to push something with our ID, so arc clone ID, as well as the unset waker. Cool. And then here we set the ID. So here we actually need ID is equal to arc new atomic usize new. Right, so here we have we allocate a new ID, we push that in. That makes sense. Probably. Maybe this doesn't have to be an atomic, actually. Because when we're modifying this vector, we're going to need a lock of some sort anyways. So maybe what we do here is instead of doing arc atomic usize, let's move back to the hash map version of this that just has like an incrementing U64 forever. So this hash map U64 to a option of a waker. And back to the ID that's a U64. And maybe what we'll actually do is we'll have a struct inner, wake up list inner, that has this stuff in it. And then out here we'll say inner is spin lock protected. That seems reasonable. So now we just need to pull in our spin lock, which comes from our utilities, spin lock. There's a lot of debug things going around, so let's just get rid of that. And then here we also need the hash map implementation, hash map to be imported, which I think comes in like, yeah, here's fine. I guess maybe here's where it belongs in the hierarchy of things. Okay. So here our ID starts at 0. Our wakers is empty hash map. And then we say that our inner is equal to spin lock of inner. And what happens next? We just say wake up list inner. Okay, so now we have like this like list of wakers that we can register with. And so now when we like request a handle to it, we create a new ID. We first lock the inner. And here we say inner.id plus equals 1, let id is equal to the inner id. So the idea here is that we've like pulled our own id. And then here we say inner wakers insert id none, right? So we have a empty waker at this id at this point. And then we return a wake up handle with our id, which is now back to being 64. Okay? Okay? Very good, very good. Okay, so now when we register a waker with this wake up handle, this guy's going to need a reference to the inner actually. So he's going to say inner is a spin lock wake up list inner, who needs to live for the lifetime of the parent. So inner is just self.inner. Great. So now we have to like shove lifetimes all over the place here. Great. And what happens now? On register, we say self.inner lock. Then we say inner wakers insert at what? Self.id. We're going to insert the waker. We actually don't need this to be an option waker because in the case where we haven't registered a waker yet, there just won't be one in there. And so here we can also take out the option somewhere. Where did it go? Here we don't insert anything. Great. And on drop, we say inner.waker, or we lock the mutex again, and we remove our ID. There we go. Okay, so I think that's it for the like handle side. So we register our waker and we drop it, and then we just need to make our like notify function. So we just grab one element at random. So first we lock the mutex. So we say let mute inner, or we don't need to say mutable. Let inner is equal to this. Inner dot. We get a waker by saying what? Inner dot dot wakers dot get, or iter next. So we get the first element. So we say let wakers equal to this, and we say if let some wakers equal that. So if there's an element in the waker array at all, we wake it up. Which I think we need to do this. Yeah, that looks right. That looks right. And here we need to throw an A in here. And I think that might compile, actually. We're close. This atomic U64 still doesn't fucking exist. Great. That surprisingly compiles. I thought this was going to be harder than that. And now, I guess all we have to do is try using this. And it might actually come for free. So let's run release and see if like any of our existing problems got fixed. This one is a sleep problem, so that makes sense that that didn't solve anything. Can I test with maybe netcat? So neither of those were fixed by that. But that's actually not surprising. I kind of identified this mutex guard as a broken thing, but in reality, we didn't actually confirm if either of the problems that were, like any of the problems we're observing are related to that. So let's commit checkpoint, wake up list in mutex guard. And And probably what we want to do is we want to try to like propagating this same pattern to somewhere else. So we know that our game loop, well, I know that our game loop is not being woken up correctly due to a sleep problem. So let's kind of like walk through what happens there. So okay, so we register wake up times with the sleep subsystem, but we don't register wakers. Oh, we do register wakers. We do wake up those guys. Oh, but we never propagate with the service. Right, okay. So there's a sleep subsystem. We have a service loop. Service loop. There's an interrupt handler. And a, like, requester. The sleep requester talks to the service with like mutex protected multi-thread safe code, and the interrupt handler talks to the service through like a single immutable reference thing. And so if I remember correctly, where we got to at the end of last stream was that this is getting propagated correctly. This path of like waking from the interrupt handler is getting propagated correctly, but this path here of propagating from the service to the interrupt handler is not working correctly. Let's see if I can prove that somewhere. This guy is using a time waiter who waits for... right. He waits for the wake-up times to have an element in them, which means that somewhere somebody's pushing into this guy. The requester is pushing into that guy. And he needs to wake up the service here. So the wake up service needs to have some sort of wake up mechanism. So I think the way we were doing this the other day was we have a service waker is an atomic cell, I think. An arc atomic cell of waker. So the idea is that like we have this like thing that we can update atomically, this like single value, and we have a shared reference to them, and we stick that shared reference both into the person who's requesting wake ups, as well as the person who's doing the service. And what we want to do here is in the wake up service, when we have our service waker is a arc atomic cell waker, and we put this guy into the time waiter. This. And this guy, he registers him like the waker with this shared value. So he'll say, my service waker is a reference to an atomic cell, and when I pull, I just say service waker store the waker that is associated with this task. And then this gets propagated all the way to the wake up requester, like this. And he now knows if he has one. He says a self service waker get. If he has a waker in there, he has to wake up the service. Great. Great. And now all I have to do is like propagate this properly. So so here we say service waker's arc clone this. We check that we compile, which we nicely do. And I think now we should see our game progressing. Nice. Nice. Very nice. So fixing that sleep fixed our our video game, because his game loop was relying on those sleeps being propagated. So now we have made sure that the correct futures are being woken at the correct spots. Very cool, very cool, very cool. Let's see what else is missing here. So here, if I try to talk to our TCP subsystem, we're still broken. So let's start looking at that. So we'll say sleep subsystem fixed. And we'll say that this will happen around 35:20 in the stream. And this happened at, I don't know, time in the stream. And now we're working on fixing TCP wake up. Okay. So let's quickly do a add-u, get commit-m, checkpoint. We'll call this sleep subsystem fixed and mutex waker list. Okay. So let's start looking at the Ethernet stuff. So in our main, in our demo, we have a let's start at the Ethernet layer. So here we have our Ethernet driver. He has a read function that calls this like callback on every time it gets a packet. And let's see if this is running. So we'll just say here, hi, packet received. Run release. And we are getting some packets here right now. And if I try to connect with TCP, we are in fact getting Ethernet packets in. So that's a good sign. What are we making it to the TCP subsystem? So here we might be calling TCP handle frame. And what does this guy do? So let's think about this. It's likely that what's happening is that the TCP service isn't getting called. So let's just say print line TCP service. And on each packet that comes in, we should be seeing our TCP service update, but it's not. So maybe I would probably bet what's happening is that the Ethernet subsystem is like sending over some TCP packet stuff to the TCP service, who maybe isn't being notified correctly. So we have to think about who is supposed to wake this guy up. He has some sleep stuff, maybe timeouts. Also he has these like connections. So on any TCP state update, this guy has to be called again, probably. Which is handled from the Ethernet side. So here, he needs to do probably like the same wake up list shit as we had in the mutex guard. Probably. Yeah, so he updates the TCP state machine. And he has to propagate that somehow. Propagate that info. Man, this stuff's complicated. I did not do a very good job of cleaning this up. So I guess let's, what does all this do? He returns a future here. Maybe let's just see TCP state machine update time. Let's just make sure that this is getting called when I do my netcat stuff. Yeah. So every time he gets a message, he does try to update the TCP state machine. Great. Probably each... let's look. I can't remember how this works. Okay, so he has like sleeps with wake ups. Interesting. So he has a timeout value that he registers a wake up with, but that's actually on the wrong future, I think. Yeah, I would bet that this wake up is supposed to be handled like, so we send a TCP response to like an incoming frame, and we want to say like try resending it if it fails, like, you know, in 10 seconds, let's try resending. But the resend is not handled by the Ethernet frame callback. It's handled by the service callback. So let's just put a fix me here. Timeouts should be handled by the TCP service future. But that's probably not the problem we're seeing here. We're not seeing any timeouts. We're seeing something not get propagated. So I'm seeing a channel here. That's interesting. This async channel, what do we have here? I bet this is related. Yes, so probably what's happening is we're sending info over this channel to the service side. Right when we like receive a message, we send that over to the service, and the service propagates that to the correct TCP port listener. And here we're not waking up when we do a send. So probably here, I think our sender and receiver are single sender, single receiver. And so probably all we have to do is in here, we have to store the waker. So we'll make a new inner struct. And he's going to have this vec_deque for sure. But he's also going to have waker. Like this. So here we need use core task waker here. And then here we're going to have RC mutex inner. Like this. And this is also going to be the receiver is going to have a inner here instead of vec_deque. And also this waiter is going to have an inner instead of a vec_deque. This inner thing is going to be called Q here, which means that here we set we push back in the queue. This is actually fucked. This is wrong. So our mutex is an async type, but we also need to be notified. No, that's right. That's right. Okay, cool. So we get our guard, and if we get our guard, we set this to the waker. We inform the other side that the waker exists, and we also try to look at the queue, get value from it. Great. Here our inner is an inner with a waker of none and a queue of vec_deque new, like this. And then here we mutex protect it before giving him to the sender and the receiver. Okay, and is that it? That might be it. So let's try. We are still not getting TCP recalls. But I wonder if there's a way for us to test where we're supposed to be. So, let's think. So here, we are sending a connection to our listener. Oh, oops. On send, I have to wake up the waker. So we'll say let inner is equal to self.inner.lock.await. And then here we say on the inner thing, we push back the value and then wake up the waker. What didn't like there? If let sum waker is equal to inner.waker. Then we wake by ref. And probably here we need to do this by reference or else it gets angry. Yeah, let's try that. There we go. Okay, so that's one side working. Is we are now at least receiving data, TCP data. We're just not sending it back. So fixing that channel fixed part of it. So we'll say fixed async channel was at around 4607, and I guess this is kind of like a subset of TCP. Okay. We'll checkpoint this as well. Fixed async channel notification. Great. Great. So now let's see. We're seeing that our kernel. We are seeing that we received TCP data. So this part's working. We're getting the data. Now, where the right side though is not working. So this is using a sender. Great. Who is using our async channel, which we supposedly just fixed, right? But who is the other end of our TCP connection? TCP connection has a TX out is associated with RX in or RX out, I guess. And who uses this guy? Connected state RX. So this guy should register the waker with the connection. But maybe we're never getting there. Let's just say print line polling. And let's just kind of see where this is called and where it's not. So he's pulled once at the beginning. And he's never called again. So we probably are missing like some sort of initial service update thing. So here we try to lock the mutex, and let's kind of see where we return pending. Polling to poll pending polling 3. We'll say down here. So we get through all 3, and then we are never called again. That's interesting. So here, probably what happens is we get the guard. We get the guard. In the guard, there's probably nothing in here. Polling loop. I would assume that like on our first iteration, we have no TCP connections to service. Yeah, so we see these like polling loops, and we never get into the like actual connection stuff. And so what happens is we register a wake up with the mutex. The mutex locks though, so we don't have to be woken by the mutex guard drop. And instead we have this like the data that's protected by the mutex is modified, and we are never woken as a result. So on modification of TCP states, this like by the Ethernet handler callback, we need to tell our future it's time to run again. That makes sense. So what the fuck is this? Wake up request. Oh, this is in sleep. Oops. Sure. Okay. So here, not here, here. I guess on every frame for now, let's just say on every single frame, we will request a service update. So here we have all this stuff. And here we can just say self. We must have some sort of like waker. We'll call this the service waker. Like this. So he's an atomic self type waker. And here he just says if let some service waker is equal self dot service waker dot get service. We try to wake it. Otherwise we don't. And now in our service function, we need to register the waker. So we go like this. Great. Did I spell service wrong again? Servica. I sure did. This is service waker. Now this polling function needs the waker that it wants to register, which is an atomic cell of waker. Something that we can modify. And then here we just need to register. So we'll just say self.service self.waker dot, I think it's store load set. What am I high? Oh, we don't have the, it's not imported, so it doesn't know. So we have atomic cell, we need to import that. And we also need to import the core task waker. And here, now we should have a store. Here we go. Yep, and we store the context, the waker for this future that we got. TCP, we need to construct this service waker somewhere, so it's probably in here. Is a atomic cell new. Very cool, very cool. Okay, so now what I hope to see, very sick. Let's go! Okay, so what we're seeing now is that the TCP state machine is getting correctly updated after the service loop is run. Very good. Or sorry, the service loop is running after the Ethernet callback is run. So we've correctly like tied those two futures together. Very, very cool. Very cool, very cool, very cool. Are there anything else we want? So print line here, I guess. We need to clean this up a little bit. Go around the release, make sure that none of those have leaked through. So we'll netcat test hello hi. Okay, and then I think we had like a UDP listener as part of our demo. So, oh sorry, let's commit this. And we'll say this is a TCP, we'll say this is a checkpoint, TCP wake up working correctly. That's a lot of typos, but I don't really care. And this is done at 5440. Okay. Very nice, very nice, very nice. Let's look at our other demos. So in main, we have our TCP echo, TCP service. We know that those are like working correctly to some extent. We have the initialization demo. So that's printing out all this stuff, which we also know works. And so the only one we haven't really checked is this like send UDP feature. Okay. So otherwise, we've tested the game, we've tested the wake up service, we've tested the RTL 139. Everything else seems to be working correctly. So we just need to make sure that this like UDP send still works. Which sends a UDP frame to port 6000 to 192.168.2.1. So I think I just need to start up netcat-u-l on 6000. And on boot, I should see a UDP message come through, which I do. Okay, so I think all of our demos are working correctly. I'm sure that there's like other bugs that have like crept in here, but there are no like super fucking obvious ones. So I think I'm happy to kind of call this complete for now and look into this more later as problems show up. I'm sure we'll find them. And if we don't find them, then they're not problems. If I cover my eyes, then the world doesn't exist. No object permanence. Okay. So we'll just say we did like one more quick change here to like avoid pointless rename. Great. And yeah, I think I'm happy with that for today. Short stream. But we did get what I wanted to get done. Probably what's up next is we're working towards multi-core support. So either what we're going to do next stream is probably either start making sure that all of these demo features are multi-core safe, or we might start trying to enable CPUs. I'm not really sure yet. I'll think about that. Thanks for watching. If you enjoyed what you saw, I upload to YouTube what we stream on Twitch like every day, or most days I should say. There are some days where I skip. If you want to catch me live, I'm on Twitch at around like 1 or 2 p.m. Pacific time. I usually stream for like 1 to 2.5 hours depending on how much work there is to do. And yeah, we'll just keep going on this. Yeah, we're just gonna keep going. So feel free to come back, tune in, catch me live, catch up on YouTube, whatever. Thanks for watching. Catch you on the next one. Bye!